Continuing from the chapter of sequences, let's move on to quadratic sequences. So, quadratic sequences are like sequences that include any possible term. They could be identified by the fact that the differences between each term are not equal, however, could be found by the second difference. So let me show you what that means. So here we have is an squared plus bn plus c. This is the formula, or basically the nth term of the quadratic sequences. Now we have a little example here. Let's see how to solve this step by step. Now let's get the difference between each term respectively. So 6 to 11 is plus 5, 11 to 18 is plus 7, 18 to 27 is plus 9, and 27 to 38 is plus 11. Now, as you can see here, the gaps or differences between each term is not constant. So therefore, we are eligible to create a second difference. So that is plus 2, 7 to 9 is plus 2, and 9 to 11 is plus 2. So now we have a constant difference for the second difference. Now, let's see how we can use algebra to solve the nth term of the quadratic sequence. Now, it's a little bit of algebra. So, this is referred to the second difference. So, this is the second difference. This is the first difference. And this is the sequence. Now, let's solve the nth term. So, what we have to do is, for the second difference, you're supposed to equate 2a to the first term to the second difference. So we have 2 in this instance. So 2a is equal to 2. So therefore, a is equal to 1. Now let's apply a is equal to 1 to a different scenario. Now we have 3a plus b is equal to the first term of the first difference, which is 5 in this case. Now we know that we can't solve this because there are two unknown variables. So since we have a is equal to 1, we can simply plug in the value of a here. So that's 3 into 1 plus b is equal to 5. Now I'm sure we're able to solve it. So now we have 3 plus 2, so that's b, is equal to 5. So therefore, b is equal to 2. Now let's solve the third and last unknown variable, which is c. So as a part of this, sequence nth term, c is the last unknown term here. So let's solve it. So the formula for it is a plus b plus c is equal to the first term of the sequence, which is 6 in this case. So a, as we know, is 1, and b is equal to 2, and c is unknown. So 1 plus 2, 3, plus c unknown is equal to 6. Now let's solve for c, and c is equal to 3. Now let's simply plug in these values for a, b, and c respectively into the formula. So the formula here is an squared plus bn plus c. Let's plug it in. So we know that n squared and n is always kept there. So a is equal to 1, b is equal to 2, and c is equal to 3. Now with this given, we have our official formula for this quadratic sequence. N squared plus 2n plus 3. Now let's approve this and test it. Alright, now let's choose the second value, for instance. So our second value here is 11. Let's see what we get here. So it becomes 2 squared. So that's n squared, and n is 2, plus 2 into 2. So as I said, n is a term number, plus 3. So now let's see what we get from here. So we get 4 plus 4 plus 3. And that is simply 8 plus 3, which is equal to 11. So that works. Let's do one more test. So this is test number 2. Let's see what happens when if we have this third term. So let's say 3 squared plus 2 multiplied by the third term plus 3. So that's 9 plus 6 plus 3. That's 9 plus 6 is 15, and plus 3 is equal to 18. Let's see if it works. And we're getting 18. There we go. So now we know that this formula works accordingly for this sequence. Moving on, let's move to another example. So I hope our basic fundamentals of solving a quadratic sequence would be much easier than you were before. So let's apply the knowledge we have now. So 7 to 11 is plus 4, 11 to 17 is plus 6, and 17 to 25 is plus 8. Now second difference, 4 to 6 is plus 2, 6 to 8 is plus 2 as well. So this is our constant base, and this is our second difference. So 2a is equal to 2. So 2 is regarded as the constant difference. So that's the second difference. So a is equal to 1. Now on the formula, 3a plus b is equal to the first term of the first difference, which is plus 4. That's 4. So let's use the values we have here. So a is 1, b is unknown, and 4 is the first term of the first difference. So 3 plus b is equal to 4. So b is equal to 4 minus 3, which is simplified as 1. Now we have our last unknown variable, which is c. So it's a plus b plus c is equal to the first term of the original sequence, and that is giving us 7. So let's plug in the values we have so far. So that's 1 plus c is equal to 7. So that's 2 plus c is equal to 7, simplified. So that's 2 plus c is equal to 7. So c is therefore equal to 5. Now let's input this into the formula we have here. Bn plus c. So make sure you plug in the values of a, b, and c here. So we have n squared plus n, and then these two are kept constant. Now we have a as 1, b as 1 as well, and c as 5. So now we have the formula to be 1n squared plus 1n plus 5, or you could say n squared plus n plus 5, either way. Now let's test it out. Let's try the first term itself. So that's 1 squared plus 1 plus 5. That's 1 squared is 1. 1 plus 1 is 2, plus 5 is equal to 7. And this is our first term. Now let's look at a different one. Let's look at the second term. That's 2 squared plus 2 plus 5. So that's 4 plus 2, and that's plus 5. So that's 6 plus 5, and that is equal to 11. And this is what we're getting, and we're getting 11. So now we can say that the formula is approved and works accordingly for this particular sequence.